today that is not happening by happenstance. This one I think is somewhat more strategic. Let me introduce Laura Robin Benedetti, Dan Casey. Laura was a USC grad and then a PhD here in 2001. Physics, right? Yes. And then Dan was University of New Mexico and then MIT. They work in the diagnostics group for the National Admission Facility. The first year students won't remember this, but we had a wonderful colloquium, very exciting colloquium a couple of years ago by Omar Hurricane talking about the new results on the high foot campaign, where they were now getting 10 to the 6 neutrons per shot out of NIF. It was an adiabat they knew that would come to an end, and now they're looking at other alternatives getting into inertial confinement fusion. NIF is the world's largest laser. I hope you get the opportunity to visit it at some point. It's I think one of the real engineering prodigies of the world, along with the Hubble Space Telescope and the LHC. It's really an amazing facility. 700 feet long. It's about the size of the Cal Stadium. 192 laser beams that focus 2 megajoules of energy onto a very tiny capsule about the size of a BB, frozen deuterium and tritium, and compress it to 30,000 times normal temperatures and densities. It's about 10 times hotter and denser than the center of the sun. And all of this works if you have premier diagnostics. And what's interesting, being able to look at the X-rays, look at the gamma rays, look at the neutrons, look at shock velocities and so forth. About 3 months ago, we had some visitors, sort of the very high-level engineering managers, come out and talk with Professor Bernstein and myself and say, we want your people, we want to take a deep look, a very strategic look, start engaging students at the undergraduate level, early graduate level, later graduate level. We have a list of 23 projects that are graded in difficulty, from things that are good undergraduate engineering projects to very, very challenging things for people who are on the cusp of being professional PhD engineers. We'd like to come in and tune up how you teach some of your courses. We'd like to see a little more electrical engineering. We'd like to come give courses, classes inside your courses. We'd love to give seminars. We'd like to have your students come out and get involved in group meetings, and we're willing to resource it. And by the way, we're willing to hire 2 students a year for about 5 years out and beyond that. This is a phenomenal opportunity. This is really NIF creating a pipeline in a very strategic way. This was music to our ears. So as part of that whole foray, we've got this colloquium today where you're actually going to hear about some of the engineering challenges. So I'm going to turn it over to Laura and Dan right away. So thank you for coming.
Thanks for that introduction, Carl. So Robin and I are going to split up the talk between the both of us. We know a lot about X-ray and nuclear diagnostics, so hopefully we can answer most of your questions. And what we'll be talking about, the title anyway, is peering into thermonuclear plasmas at the National Admission Facility. So NIF was built to demonstrate inertial confinement fusion in the laboratory. Our goal is to achieve ignition, which requires very extreme conditions. You have to accelerate capsules to very high velocities, hundreds of times faster than bullets go. Very high densities and temperatures, higher than you would find in the core of the sun. And in order to understand these conditions that we create, we have to have world-class diagnostics, and we have to use them to understand those conditions. So controlling and diagnosing these implosions in their final phase has proven very challenging, particularly with regard to understanding the shape and symmetry of these things and keeping perturbations from distorting those shapes. But it's also very interesting and exciting. And as Carl mentioned, we developed a national diagnostic plan, which was sponsored by DOE, to invest in new diagnostics and improve the ones we already had. And we're really looking to hire the next generation of creative scientists and engineers to help do this. So just a little bit about fusion, in case you haven't heard a lot about it. What we're trying to do is combine isotopes of deuterium and tritium to form the more stable helium nuclei and neutron, and that process releases energy. So if the alpha particle or the helium nucleus can stop in this plasma, then it'll deposit its energy, And if that exceeds the losses of energy in this plasma, which are the neutrons which escape, there's thermal conduction. Since this is a hot thing surrounded probably by cold stuff, then you'll have thermal conduction leaving the plasma. And X-ray radiation and just thermal, expansion, PDV losses from this system. If fusion energy can exceed all of those losses, then the energy content of the plasma will go up, and you can get a thermonuclear runaway, which would lead to ignition. So if you just simply balance these power losses, fusion power versus the energy losses that you have, you can find that there is a criterion, Lawson's criteria, on the pressure and the amount of time, or the confinement time that you have that pressure. There's a requirement on the product of those two, and if you can exceed that product, which is a function of the plasma temperature, then you find that you have favorable fusion energy power balance, and you can achieve a running away thermonuclear ignition of your thermonuclear fuel. So that's our goal, is to exceed this condition. The way we do it in ICF is we use lasers. So we have lasers that irradiate the inside of a high Z horon, which is basically just a cylinder of gold or depleted uranium. The lasers make X-rays inside this horon, which fill the entire cavity. Inside of there's a plastic capsule, and inside of that plastic capsule is a DT, cryogenically frozen shell. And the X-rays that are made by the lasers then ablate the plastic capsule outward, which sends the remaining cryogenically frozen DT shell imploding inward. So this is a movie of a simulation of this process. So what you can see is the lasers will go through, they have to burn through the helium gas that fills the horon cavity. They interact with the gold wall here, and the gold wall starts moving in. As X-rays fill up this cavity, it starts to send this plastic shell moving outward, and then after about 22 nanoseconds or so, the laser power hits its maximum, and then you see that the capsule itself just implodes inward very quickly. The principle behind the imploding shell is very much like a piston. So the shell delivers its energy, which it gets from the X-ray drive to the hotspot, by compression. So the X-ray drive will accelerate the capsule imploding inward to some velocity v. We'll call this the peak velocity. And then at some point at the end phase, or at the stagnation, you'll have a scenario where there's a hot spot surrounded by a motionless DT shell. So you can just do a quick energy balance of what this situation looks like, and you can say, okay, well, at peak shell kinetic energy, that energy of the shell is 1/2 the mass of the shell times the velocity squared, and that needs to end up being the hotspot internal energy, which is just 3/2 times the pressure times the volume, or the radius of the hotspot cubed times the pressure, plus whatever ends up not making it into the hotspot. It's not a perfect piston, so there's going to be energy trapped in the shell. It's going to be in a 3D perturbation that might be growing, so we'll have this term here that we call the residual kinetic energy. And the final state of the hotspot is this underdense, hot, gaseous region surrounded by a cold, dense DT shell. So the shell mass itself provides the inertial confinement that holds the hotspot in place. And we can calculate what that time scale is just from Newton's law, where the mass times the acceleration is the pressure of the hotspot times the hotspot surface area, which is the force moving back on the shell. For a thin shell, we can say that the mass at stagnation is the areal density of the shell, or the rho r, times the 4 pi times the radius squared. And we can solve for a characteristic time scale, tau, which is just the square root of the radius over r double dot, and that's a function of rho r. It's a function of pressure and radius. If we combine this expression with the expression that we derived on the last slide, we can calculate what p tau is for an ICF type of experiment. It's a function of the areal density of the stagnated assembly, the fuel assembly. It's a function of the peak shell velocity. And it's also a function of this residual kinetic energy term, which is really just the coupling of the shell to the hotspot. So what this analysis tells us is that we need to go very fast. We need high implosion velocities. They need to end up being very high areal density in the end. And we need to make sure we have an efficient coupling between the shell and the hotspot, meaning we need things to be round. We need to minimize this residual kinetic energy. So now I'll hand it to Robin.
So this is the flashy, pretty pictures part of the talk about NIF. So the National Mission Facility was built to achieve controlled inertial confinement fusion, as Dan said. This is a beautiful sunset picture of the outside of the building. As you've learned already, it's a large building, 3 football fields in size. The important one being here in the middle, of course. So if you pulled the lid off, we have a building at the end for assembling optics, a building at the other end for building and assembling diagnostics. And in the middle, we have capacitors, so we have to store up a bunch of energy for each laser shot. Then we can amplify the laser, comes across here through the laser bay. And here, all the lasers come together in the 10-meter target chamber. And all 192 lasers have to be delivered from this giant building to the very center of our target chamber with precise energy, precise timing, and precise pointing. So it's a very large engineering challenge. This is the first of many images you'll see where we have humans as our scale bars. So this is the laser bay with the work crew in it. So these are each individual laser beam tube. And then here's a picture of the target chamber as we were installing it into the building. So this is our 10-meter chamber with the square ports are where each laser beam enters. And a lot of these round ports going across the side or around the chamber are used for diagnostics and other control operations. So our whole experiment takes place in the target chamber. Everything has to get in it this way. And then, of course, the whole 10-meter chamber is evacuated. So this is the target chamber in situ. Again, these are each one of these paths is one of the 192 beams of the laser. This is a close-up again of the final part of the laser assembly entering the target chamber. You can see it's quite complicated. Each beam tube is filled with argon. We have precise pointings and mechanical fixtures in there to get the final pointing into the target chamber. And of course, this isn't just high tech, it looks high tech. And as a result, Star Trek filmed here. So Star Trek, the Into Darkness, the laser bay was Khan's area, and the target bay was the USS Enterprise. So next time you're at the video store, if you feel like a little scientific jaunt, the video store. Oh, that's kind of old. Next time you're on Netflix. Okay, so here's another view. Note the human for scale of inside the 10-meter target chamber. And now that it's built, it looks like this. So it's 10-meter chamber, each of these laser beam ports. Here's the target, 1 centimeter to 1 millimeter, at the center of this 10-meter chamber. So the target is inserted here on the target positioner, and these are different. This is the target, the TASPOS, the target viewing system. So all this giant building, 3 football fields, all comes down to getting the lasers precisely on this small target.
Is that 10-meter diameter or radius?
Diameter. So here's a photograph from an actual NIF shot. It is false color. It's not actually purple and orange, but
Still probably.
it's probably closer to white. And here are diagnostics inserted into the target chamber to see the implosion as it's happening. So the target chamber and the building are large. The target itself is small. This is a photograph of one of the gold hole ROMs. So it's a hollow cavity that's about 1 centimeter, in which a 2 millimeter capsule sits. So for scale here we have a dime. So the capsule is similar in size to Roosevelt's nose. So this is a plastic shell, and inside the shell, this is an X-ray of a target. There's layers of plastic with some silicon dopant, and then right in here you can see the edge of the solid layer of DT, and then inside there's the vapor pressure of DT gas. So it starts out here at 2 millimeters diameter, has to compress 35 times in its implosion. The aim is for something nearly spherical. So this is an X-ray emission image from an implosion. So ideally, we want something that's nearly spherical over this large implosion. But here's one of our high precision models of what the capsule actually looks like in an implosion, and you can see it's far from spherical. This is density, and we think this is velocity, and the surface is an isothermal surface over here. So this is one of our big challenges. We need it to compress spherically and uniformly. We think that some of our implosions look like this. The challenge is to be able to diagnose that, to see exactly how it's behaving in the implosion. So, as Dan said, to achieve ignition, we need to go very fast to achieve high velocity. We must be highly compressed, have a high ρr of the target, and be very round in order to minimize the residual kinetic energies and any other perturbations. So in order to know where we are on that path, it's probably pretty clear. We have to be able to measure velocity, we have to be able to measure ρr, and we have to be able to measure symmetry and yield. So for the rest of this talk, we're going to talk about some diagnostics. Dan's going to talk about neutron spectrometers that we can use to measure ρr and yield, and neutron activation detectors to measure the symmetry of the compression. I'm going to talk about some X-ray diagnostics, X-ray street cameras that we use to measure velocity of the implosion, and X-ray framing cameras that we use to measure the symmetry of the implosion. So we're making constant improvements to these detectors. The National Diagnostics Plan is part of that, and the idea is to make our understanding more robust, more precise. We're constantly evolving all of our detectors. Oh no, I have one more. So this is an example of the target chamber and the X-ray diagnostics. Some of the X-ray diagnostics that we use. You can see our X-ray diagnostics are basically all distributed along these ports around the side of the target chamber because X-rays don't go through the target chamber wall. Many of the diagnostics are just right here at ports fixed on the side of the wall. But we also have 3 DIMMs, diagnostic instrument manipulators. You can see an example of one here in the North Pole. And we can actually use that to take an instrument and insert it all the way into the center of the target chamber so we can get a close-up look of the implosion. So the 2 diagnostics I'm going to talk about are actually on DIMMs in order to get close-up view of the implosion. Now you're up.
So as Robin said, the X-rays don't go through the chamber, but the neutrons do. So a lot of the neutron diagnostics are outside the target chamber. We'll talk a little bit about the magnetic recoil spectrometer, which is shown here. It's just above the equator, if this is the target chamber equator here. We have several neutron time-of-flight diagnostics that we'll talk a little bit more about. There's a handful at the equator that are actually not just outside the target chamber, but outside the target bay itself. That provides good collimation and low backgrounds from neutron scattering around on other things. And we also have a neutron spectrometer that was recently installed on the South Pole here, and we're installing one in the near future on the North Pole so that we can get a good coverage of the directionality of the measured neutron spectrum. And that's interesting because the ICF Neutron Spectrum provides quite a bit of information about the implosion. It tells us the total fusion yield because for every fusion reaction there's a neutron, so we can count the number of neutrons and from that get the fusion yield. It tells us the temperature and the areal density. And the way we get that is, we were talking earlier about how each reaction makes a neutron. Each fusion reaction has 17.6 MeV from the DT reaction, and the neutron takes 14.1 MeV of that. But the plasma is having some thermal motion of the ions. So there's going to be a Doppler shift depending on what the relative motion of those ions were with respect to your spectrometer line of sight. So if you average that over all the reactions that happen, that ends up being a Doppler broad width. So this is a simulated neutron spectrum, and yield per MeV is a function of neutron energy. The 14.1 MeV DT neutron is this peak right here in the red region. The width of that peak tells us what the plasma ion temperature was. And then we just use this equation right here, which falls right out of a cross-section type of calculation. Now, there's actually enough mass around the hotspot that an appreciable number of the neutrons will scatter on their way out. This is the scattered neutron spectrum, so we measure that. This region here in green is a region that we focus in on in particular. We can relate that to the areal density of the implosion by looking at how many of the neutrons scatter. That's directly proportional to the implosion areal density. So the way the neutron time-of-flight, or NTOF diagnostics work is using time-of-flight energy dispersion. These are current mode simulators. Since we make all of our neutrons in a single burst, they function in current mode. And we use their time of arrival to the detector to infer the neutron spectrum. So in this cartoon here, we've got an implosion, and some distance away, d, we have an NTOF detector. And so we can calculate what the energy of a neutron has to be in order to arrive at a time of flight t, just from the distance from the detector. It's just 1/2 the mass of the neutron times the d over t squared. And the detection mechanism for the NTOF detectors is scintillation. So we have scintillators which detect recoil scattered protons in a scintillator, or charged particle reactions. In this case, this is a bibenzyl crystal scintillator. And this detector right here, which is the South Pole detector we saw earlier, there's a scintillator in the center here in this box, and that's coupled to 4 light guides. So the neutron from the target will go down through a collimator, hit the scintillator, and then the light produced is taken to 4 separate photomultiplier, or PMTs, where they are digitized, the signal's digitized and sent to a reporting system. This is a time-of-flight spectrum taken from an actual NIF shot. You see a prominent peak somewhere around 450 nanoseconds. This is about 20 meters away from the target, so this is a 14 MeV neutron peak. And then down here you see the rest of the spectrum from scattered neutrons. Another detector we have is the magnetic recoil spectrometer. It uses deuteron recoil dispersion in a magnetic field and CR39 nuclear track detectors. The principle here is neutrons come from the target, they hit a foil, which is just a plastic, deuterated plastic foil, some distance from the target. Elastically scattered deuterons from neutron elastic scattering reactions will then go down into a magnet and are dispersed by their momentum, so that the highest energy deuterons end up on the furthest end of the detector array, and the lowest energy are deflected the most in the magnet are at this end of the detector array. The CR39 detection mechanism is basically the charged particle will create a damage site in the plastic that is revealed through chemical etching. The damaged sites are revealed faster than the bulk plastic. That makes little pits that you can see in a microscope, and each pit corresponds to a deuteron. Each deuteron corresponds to a neutron, and where that pit was tells us the neutron energy that created the original event. Kind of an interesting fact is CR39 is not the primary market in neutron spectrometers at NIF. It's actually what is in light eyeglasses, so I'm actually wearing CR39 right now. Where we're going with this is to try to time resolve this same process. So the MRST is the time resolve version that's being designed right now at MIT by Johann Frenje and one of his graduate students, Brandon Lahman. So they're working on coupling this same scheme where neutrons hit a deuterated foil, make deuteron elastic recoils that then go through 2 magnets, are dispersed and focused onto a scintillator array. So this array of scintillators would then be coupled to some kind of fast optical readout, and most likely a street camera, which Robin will explain the physics of in a bit. Another interesting nuclear diagnostic that's routinely used is the flange nuclear activation detector, or FNets detector suite. This is to measure the anisotropy in the unscattered neutrons, and it's very high precision, of order 3%. And this is interesting because, like I said earlier, neutrons scatter appreciably on their way out of the implosion. And our implosions are not symmetric, so we have areal density asymmetries. We have, in this case, a simulation which shows more density up here. And so when neutrons go through this higher density region, they are attenuated more than they would be if they went through the lower density region. And you can calculate exactly what this attenuation is. It's just this formula here, where the yield as a function of solid angle is just the birth yield times this attenuation factor, which is e to the negative rho r of that line of sight times an effective scattering cross-section. We place 17 detectors around the chamber at different ports. These detectors are zirconium, so there's an end-to-end reaction, which is a very high threshold reaction, where you make an unstable zirconium-89, which has a very long half-life. So you can place these detectors on 17 different ports, and then sometime after the shot, collect them, take them to an offline counting facility, and then measure the gamma rays that come off of the zirconium-89 on a high-purity germanium detector. Use the activation at the time you count to correct for the activation at the time of the implosion, and get the activation map. And that's what this plot is here. This is a measurement of the activation at the 17 different lines of sight for a recent cryogenic implosion. And what you see in this color scale is the yield normalized by the average yield. So this is 0.9 in blue, and this is 1.1 in red. So up here in the blue regions, there's less activation by about 10%. That means there's more areal density. Here in red, there's higher activation, meaning less areal density. So there's like a little thin spot in the shell, and there's something which looks like polar ice caps on this particular implosion. This is extremely useful because trying to see this type of asymmetry is not easy with other diagnostics. So this is really a fantastic diagnostic in sorting out what's happening in our implosions. We're taking this to the next level with the neutron isomer ratio detector development. This is being done principally by Ellen Edwards here at UC Berkeley. She's taking the same principle with this zirconium. So you have the zirconium end-to-end threshold reaction, but instead of taking these to an offline facility and counting them on a germanium detector, she's setting up these real-time lanthanum bromide detectors. You can see her with a detector that she's setting up right here. It sits right next to the sample during the shot. And this is an actual trace of data that she's taken just maybe about a month ago, where this axis is time and this axis is energy. So right here it is about shot time, maybe slightly after shot time, and this is almost 100 hours after that shot. And then here in the energy axis, you can see 1.4 MeV here. This is the sodium-24 line. There's a few lines out here from lanthanum reactions and a potassium-40 line. I should say that the color scale here is the log of counts. So what you're really looking for is this line here. This is the zirconium-89 line. If you take this and you plot a decay curve to it and you extrapolate to the shot time, this is what tells you the activation of that zirconium detector on that line of sight that's being used. So this is a big improvement. It would allow us to field more detectors, hopefully, and get the data faster. So this is really important.
So we can't understand everything with neutrons alone. So we use a lot of detectors that are based on X-rays. X-rays are useful in part because the implosions are hot enough that they are emitting light primarily in the X-ray region. So there's 1 to 5 keV temperatures, that's like 10 million Kelvin, means that they're emitting in the 1 to 20 to 30 keV photon energy range. Also, X-rays make incredibly useful probes to look at materials, so we can do radiography, we can do spectroscopy, if we can probe our samples with X-rays and then measure the X-rays. So we need photon energies 1 to 30 keV, we need timescales of a few nanoseconds, and we need length scales of a few tens of microns. And I'm going to talk to you about some X-ray street cameras that we use to measure the velocity of implosions, and X-ray framing cameras that we use to measure the symmetry of implosions. And what we need in these X-ray diagnostics is we need very high sensitivity to measure on the scale of this short time scale with a high spatial and high temporal resolution. So our workhorse detector to get this kind of resolution and sensitivity is called a microchannel plate. It's a device that basically amplifies an electron signal, turns photons into electrons and amplifies them when a voltage is applied. The primary market for this device is actually night vision goggles, and after that, X-ray telescopes. So Xray Diagnostics at NIF are a small subset of the market. The way it works is this, that it's made of leaded glass, but it's actually mostly made of air. So it's 50 to 80% air in tiny little channels in a little glass plate. The channels are about 10 microns in our case, so that's what gives us our small spatial resolution. When you coat it with a conductor at the top and bottom and then apply a voltage, when you have an X-ray hit the glass, it liberates an electron, and when there's a voltage applied, that electron gets accelerated down this channel. Each time it hits the wall, it releases more electrons so that at the bottom you have a torrent, a cascade of electrons that come out and hit a phosphor, which can then be coupled to an optical diagnostic. So this is the principal way that we are still using converting X-rays into something that we can see. In order to measure velocity, we use an X-ray street camera, which disperses the temporal information in space but retains one-dimensional imaging. So here's an example of a target. We are imaging one dimension of it, so imagine a line across your image. This is a simulation of how it works. So at the front end, we have a slit with a photocathode that turns photons into electrons. And then we have a tube with an electric field that keeps those well focused. And then here I'm going to turn on the simulation. So X-rays convert to electrons, which are accelerated down the tube. When they get here to the end, there's a voltage in this direction that deflects the electrons. So the electrons get deflected, but the voltage changes in time. So as a function of time, where the electrons are deflected to on your detector changes. So in the end, you get an image that in one direction is space, so you get this line through the center of your target, and in the other direction is time. And it's just by how much time you resolve is all a matter of how fast you change this voltage on the output end of your tube. So the street camera that we are using to diagnose velocity is called a DISC, which just means dim inserted street camera. So it's one of those diagnostics we put on a DIM and get quite close to the target in order to take good X-ray images. So here's an example of a target where we might use it. This is our whole ROM target. The capsule is in the center. The X-rays come in through the top and the bottom. And this is a zirconium foil or a zinc foil that by illuminating it with a laser, we can create X-rays. The X-rays will go through a slit on one side of the whole ROM and then be able to escape a slit on the other side to the disk. And then so here's an example of what you might see. Again, distance is in the horizontal direction and time is in the vertical direction, going from early time to late time. And what we can see is the capsule that we're imploding is indeed getting smaller. And by identifying where the edge of the capsule is as a function of time, we can measure the radius of the capsule as a function of time. Derivative of radius is velocity, so we can measure how fast the capsule is imploding. So this is our measurement of how fast the capsule is imploding. We're also making, as with all of our diagnostics, continuing to evolve the diagnostic to see what else we can measure. This is an example of we've recently coupled a spectrometer to the front of the street camera. So with this measurement, the NIF Xray spectrometer, we can now measure Xray spectra as a function of time. This is important because the Xray spectra can tell us really detailed information about the plasma conditions, the ionization states of plasma. So here is an example of data from this diagnostic, which basically is, so we have 10 different spectral windows with an absolutely calibrated spectrometer on the front of this street camera. So we can measure energy as a function of time. Here, time is across the bottom, And you can see the laser pulse is here in white, and then what you see is different emission lines of the spectrum as a function of time, manganese and cobalt. And so you can see different emissions turning on with the laser and some turning on later in time as the plasma gets hotter. I mean, this, for example, is work done by a young engineer and young scientist at the lab, Shannon Ayers and Maria Barrios. So this is another example of a new diagnostic that's being led by some young scientists at the lab. So moving on from the velocity, we need to measure the symmetry. To take a picture of the ICF implosion, the camera needs to be really, really fast. So just for scale, this is a movie of a bullet hitting a wall that's 2.2 milliseconds. So then this is a high-speed off-the-shelf camera, so we're seeing 500,000 frames per second. To get a good picture of a NIF implosion, we don't need to measure for 0.2 milliseconds, we need to measure for 0.3 nanoseconds, because the whole capsule implosion is tens of nanoseconds, but the time in stagnation is only about 1 nanosecond. So here is an example. This is a simulation of X-ray emission from an implosion. And you can see that over this 0.3 nanoseconds, things are quite dynamic, quite moving. So we need to be able to measure the images as fast as that. So if we start with a microchannel plate and we just project a bunch of images by pinholes. Pinhole optics are simple, hundreds of years old, reliable, you don't need to focus them, but if you create an array of many pinholes and thus make several images onto your microchannel plate detector, you can get an array of many images, and we use that to make what we call an X-ray framing camera. So we start with a microchannel plate, we coat microstrips onto it, so we have different strips of conductor, and then with the pinhole array, we project images of the implosion all over the detector. But then what we do is we don't, as I said before, the images are only amplified when there's voltage. So in order to make voltage, we send a very narrow voltage pulse into the microchannel plate through each strip sequentially. So then, while we are projecting an image of the entire implosion, we're only amplifying it when the voltage pulse is going across the camera. So you have a narrow pulse traveling across the camera. Each image represents one specific time. Then we can knit those images together and make a movie. So the total record time that we can have in our movie depends on how fast we can propagate the pulse. So on our cameras right now, we can record about a nanosecond. And the fastest shutter time depends merely on how fast the electrons transit through that glass pore. So the fastest we can get is about 40 picoseconds. So we can get a record of about a nanosecond, taking images that each one is a shutter time of about 40 picoseconds. And here's an example of that. So this now, compared to our bullet photo, is a movie made from each of these different frames, collected of X-ray emission from an implosion. So here what you're seeing is the implosion is getting smaller, smaller, smaller. That's probably bang time. And now the X-rays are expanding out and we see a blast wave after the implosion. So, and that whole length of movie is 0.7 nanoseconds. This, so is this fast enough? In this case, this is actually 100 picosecond record shutter speed, but we wanted to be able to get faster. Ideally, we'd have faster than 100 picosecond record. Can we do that? Can we get to the next slide? Okay, so if we can't make the microchannel plate faster, we can't make it faster than 40 picoseconds without making it too fragile. So can we spread the images out instead? So the idea is like this, like a sprint. At the starting line, all the sprinters are very close together, but if they each run at different speeds, by the finish line, they're quite well separated. So we do the same with our images. So we have a new imager called the dilation X-ray imager, uses a technique called pulse dilation to get better temporal resolution. So if we have an incoming signal of photons from our implosion, that is a few hundred picoseconds long. We convert it to electrons with a photocathode. And then we allow, right after we convert it to electrons, we apply voltage ramp. In this case, the voltage is changing from this side to this side. So with the first electrons that arrive get accelerated more, and we reduce the voltage in time so that the last electrons to come through are accelerated less. So the first electrons are going fast, the last electrons are going slow. We wait some time, and they get spread out. So whereas at the beginning, our 100 picoseconds camera speed represented this much of the implosion, now we're able to separate to collect quite a bit more images over the same amount of time. Then it hits our microchannel plate and amplifies the electrons. So here's an example of data. Dixie data is on the top. This is data collected with 10 picosecond resolution. Time is going from left to right. And the corresponding GXD framing camera with 100 picosecond resolution is along the bottom. You can see that with the high resolution camera, we see quite a bit of motion. You can see this little red high intensity image spot going sort of from the upper left to the lower right of the image. And if you look closely at the longer integration time, you can imagine that you see sort of the same thing, but you probably only see it because you know what to look for from the high resolution images. So this camera is in operation on NIF, and again, it's an example of young scientists and young engineers, Sabrina Nagel and Jay Ayers, led the project. So we are getting good data with this fast resolution camera that is telling us some features about the implosion that we couldn't get before we had this high resolution camera.
So that's just a few examples of some of the diagnostics we use, but we wanted to just say briefly how we use some of that data to infer where we are with implosions. So we showed this space before where this is the Lawson type criteria with this p-tau as a function of temperature. We're pretty confident we haven't gotten ignition yet. That's fairly obvious, but we want to know where we are in this space. And so we can use the measurements that we've talked about today to do that. So here, this is an equation which is essentially what the yield is. It's a function of the density of the hotspot squared. It's a function of the Maxwellian average DT fusion cross-section. That's just a function of the ion temperature, which we measured from the neutron spectrum. It's a function of the volume of the hotspot. That's something we can reconstruct using the X-ray images that Robin was talking about. And it's a function of how long the hotspot was hot, or the burn width. And that's something we can also get from X-ray diagnostics. And we measure the yield from the neutron spectrum. So we can just solve for what the density is. Once we have the density, we can infer quite a few things about the hotspot. We can infer the hotspot density. We just calculated what that is. We can infer what the mass is, the areal density of just the hotspot is rather than the total areal density. And we can infer what the pressure is, which is exactly what would go in this space here. So if we do that, this is sort of a scatter plot of where we have been in the past, where we are now, and sort of how we got here. So this is p-tau as a function of the measured ion temperature. At the end of 2012, we did a series of experiments, which are shown here in blue. We had a handful of hypotheses for why these didn't get a little bit closer to ignition, one of which I think Omar talked about at length a year ago, and that was that the outer capsule surface was unstable, so we had some techniques that we can do to improve the stability. Those are the magenta and the green points, so you see that indeed after making that change, the performance in this pressure tau space has gotten quite a bit closer to what you might call the Lawson criteria. We've also tried a few different ablators. So in everything in this talk we talked about plastic shells, but you can make shells out of high density carbon. That's the yellow and the orange, and those go quite a bit faster, so you can get the velocity up, and you can see, at least in these cases, that was a win. We've also shot a beryllium capsule. That's not on this space, but we're trying different things. We have a strategy for how we're going to try to get from this space to this space. We think we need better control of the shape of the shell in the hotspot, in order to have that control or to even know what the shape was, we need good diagnostics. We want to get the velocities up if we can. That's a big win. And we want to get the compression up. So we're learning and we're making progress. And this is just to show you another quick set of images that come from our diagnostics about where we think our biggest issues are right now. So this is a view of the whole ROM. These are two X-ray images that show an oblate implosion. So this is fairly pancaked, it's flat. And then you look from the top, there's sort of like a hollow spot in the center. If you combine this with images that come from the flange nav detectors, what we see are asymmetries that look like the imploding shell is actually very 2 and 3D, where it sort of pinches off in the center, and we think that's what's causing this cold spot. We think this is a significant perturbation on the overall performance because it causes the shell not to couple well to the hotspot. It increases the thermal conductivity losses from the hotspot out of the shell. So a big part of our program now is to improve the control of shape, and we just, the better our diagnostics are, the better we can exert that control. We also have the capsule mounted inside the whole ROM. It doesn't just levitate there, unfortunately. It's being mounted by this saran wrap-like membrane that is mounted at the equator of the whole ROM. And where it lifts off from the capsule, it actually imparts a momentum like vorticity perturbation that makes a very significant perturbation on the hotspot. This is a X-ray radiograph of an actual implosion, and you can see these horrible scars across the implosion are actually from that membrane, and we think that that's a very significant perturbation on the implosion and very damaging to the performance. So we're trying different things. We're going to thinner membranes. We're using techniques with the pulse shape to decrease this perturbation, and we're making a lot of progress in both of these areas. And once we solve these issues, we may find other issues. There's hot electrons that come from the laser interacting with various parts of the plasma, and they may cause some problems, but when we get there, we'll need good diagnostics to sort it all out. So just to summarize again, NIF was built to demonstrate controlled inertial confinement fusion in the laboratory. The conditions that are required in order to reach ignition are very extreme. It has to go very fast, orders of magnitude faster than a bullet. It has to be very dense. It's denser and hotter than the core of the sun. We've built some pretty impressive neutron and X-ray diagnostics, but we need better ones in order to really sort all of this out. So we have this national diagnostic plan that we've worked with DOE and with a lot of other laboratories across the United States, and we're hoping to hire people to help us do this. So thank you. With that, we'll take questions.
Yeah, your shots with the lost contour. You want to explain what the Underdecks means in there?
This 100x is supposed to signify a 100x amplification in the yield due from alpha heat. So we think some of these best performing shots up here are at a little bit over 2.
Okay, well, is this the same as like Q equals 0.01?
Well, let's see. So Q is fusion energy over input energy or something like that. I don't know. I'd have to think about exactly how that would refer to Q. I mean, the traditional definition of ignition in ICF is 1 megajoule, which is sort of...
Well, the definition of magnetic fusion is Q equals infinity. Okay, that's for starters. But also, I think that curve means that you've got a Q of about 0.01 there. I mean,
sure,
if you compare that to the one from Jeff Freiberg's book, it's way over here, starting at about, hook at about 15 kilovolts, right?
15 keV at temperature?
Yeah.
Well,
That just goes to the ozone below that, right?
Well, I mean, this contour has a very specific meaning, which is that energy that you gave to the hotspot from the shell imploding
Yeah.
has,
In other words, you're already taken a discount of about 99% on the laser energy.
yeah, I mean, if you wanted to build a fusion reactor, you have to be like way out in this space. There's no arguments there. This is really about sort of an alpha particle self-healing. I mean,
For the
the
part
NIF laser
that-
is very inefficient,
Yes.
even from an ICF standpoint. You could make lasers more efficient, but this one is
No,
particularly.
not the laser, even from the laser light entering the overall.
Yeah. Well, so the definition of ignition could be the laser energy on the wall versus
Well,
the
it
number of
seems
neutrons
the
coming out.
story-
That's what was defined by some group of people.
I understand that, but it seems your story is, well, we don't understand why 99% of laser energy isn't coupling. So we're just going to look at the 1% that does couple, and we're going to compare that to the fusion element heat.
Well, I mean, there's no question that we know we are still bootstrapping our way up
Yeah.
a long way to go.
Yeah, well, the point is that I think your best shot has been, what, 22 kilojoules?
I don't remember exactly what it is, but it's
Yeah.
up that.
Yeah, and you put in 1.8 megajoules to get there.
That's about right.
So
yes.
that's a Q of 0.01.
Okay. Fair enough. Any other questions?
How many shots per unit time are you getting? Have access to the facility and then to do the experiments you want to do?
So that's a good question. It's a function of how complex the shot is. So we can do simpler shots that might just be lasers on foils or lasers on warm targets. In principle, we can do several per day, maybe even 4 or 5 might be near a record. We're trying to get better with that. We're trying to go faster. Our more complicated experiments, like the ones that are shown on this plot, usually take about 24 hours at least, so it would be much more than a shot per day.
And we typically only do 1 to 2 of those per week, where we're filling in the rest of the time with other experiments that are telling you about implosions that are maybe not DTs. We're doing other implosion experiments that tell you about how to make high velocity or about how to control shape, but don't require making a layer. So there are a lot of experiments we can do on our way to a DT shell.
So a major program going on for years has been to take a quad of beams, compress them to 10 or 20 picoseconds as arc, and make a backlighter, which would give you one or a few snapshots. How would arc fit into these other diagnostics that you're doing, where by looking at the intrinsic X-rays, for example, you're already seeing a continuous movie? What's the kinds of things will you achieve? What is the status of arc right now?
So we're doing a lot of arc shots. We're making a lot of progress with getting, so the idea of arc is to take 4 beams and separate them into beamlets that will be able to make 30 picosecond, very narrow beam pulses. And by combining all the energy into such narrow pulse, we should be able to get more flux. So we are making progress. I don't know the exact status, but we have been doing quite a number of arc shots, and there were some wrinkles in getting the timing to work out the rest of the timing system, but I think that's been the hurdle we just worked out. I know some of the first experiments that we're planning to do with arc, the advantage is that you can get a potentially very short in time, very bright X-ray backlighter. So those velocity movies I showed you were based on needing a backlighter. With a brighter backlighter, we can radiograph a denser material. So among the first experiments we're going to do, we're going to try to do some Compton radiography where we're radiographing the fuel at stagnation. So at the very latest time of implosion, when it's as dense as it can be, to see what the symmetry of the fuel is at that time. I think the first the next experiments to work that out are in January, I think. So I think those will be the first ones where they are using the arc beam, testing the arc beam with the implosion. So that's a very high profile set of experiments that we're going to do to diagnose a part of the shell that we couldn't see. There are a number of other experiments that we're going to use that very short backlighter to look at other materials experiments where you have a high density material that you're trying to radiograph.
So you have, I think Nova used temps to hold capsules as well. And I'm curious whether there was any evidence back then that they might be bad actors, and what was it that implicated them finally so that you could focus on the temps as being the source of some of the problems you were having?
That's a good question. As far as I know, there was no evidence. I can't say that for sure. No, it was before my time. But as far as I know, it was really these radiographs that we just started taking using NIF beams on a backlighter of the capsule, where we saw it wasn't quite as striking as that particular image, but it was clear enough that wow, it looks like there might be a perturbation from the tank, capsule support tank, and that was, I think.
Yeah, I think the answer is we weren't getting these radiographs of the shell. We were getting 1D images of the shell, or we were just getting images of the implosion. And now that we get the shell in flight, this perturbation that has a defined shape is most correlated with where the tent happens to hit the shell. I don't think we had the ability to see that before.
And I think that makes using the arc beams as a backlighter all the more exciting. I mean, who knows what we'll see when we take our first images of what the shell looks like.
Our speakers are going to stay around here if anybody would like to talk to them, because this really is an opportunity. This is part of a long-term engagement for students to get involved here if they would like to view this as a thesis project and as a career opportunity. So you'll be around here for as long as you wish to talk and perhaps see the facility and begin to get involved in research. Further questions, or should we? Don?
On the slide you had before this one, is that Lawson criteria is what you were talking about relative to that slide, have to deal with that 100 times there? Yeah, 100 times means that Lawson criterion line is 100 times closer than it really is?
No, so Lawson's criteria is very specific. I think, as you were saying, it's at a particular temperature where it's minimized. This is sort of the spirit, I think, which is that as you cross a boundary, there is a regime where alpha particle self-heating is very important to the overall energetics of the implosion, and this contour here is where alpha particle self-heating has contributed 100 times the energy that the shell was moving towards.
So
that's peak velocity, peak kinetic energy.
So where, relative to those points, where is the real Lawson criterion? Where is the line that separates?
It's a very good
emission
question. I didn't
from-
actually know the answer, at least not for sure until I plotted it, and it turns out that it's very close. That this is not a log plot, and this is, but if you were to put that line, which is what you would get right out of Jeff Freiberg's book, and put it on this curve, it's very close to this. A little bit different shape. This is very close to, however you want to define it, an alpha self-heating ignition type burning plasma emission.
So to follow up on that, you're saying so the alpha being reported, that's relative to the energy that was imparted by the implosion itself. So let's forget the lasers, right? That's just the energy that actually got there.
Yeah.
Okay.
Yeah, that's right.
But the lasers don't matter, right? Like the energy just magically came from somewhere. That's
So-
what actually got there. I mean, relative to that, right?
Yeah, that's right. So this curve is 100 times the energy that the shell had,
Okay.
and there was a lot of energy that was already thrown away
Okay.
by the time you got to this point. But there's one part of ICF that's a little different than MCF, which is that when you actually start the burn in a hotspot, the idea is that once you get self-heating going, it burns through this cold shell. It's sort of like almost like a diesel engine. So you start a spark, but then you burn up this fuel there, so that if you get what is referred to in the literature as ICF ignition, you can get fusion energies that are of order the laser energy that hits the hole on the wall. Now, from a fusion energy perspective, if you wanted to make an ICF reactor, you'd need quite a bit more than that. So what they talk about in the ICF literature is gains. You need gains of, I'm not exactly sure, but at least 100 or maybe 1,000 or something. And so that's where you would want to go to try to make this into some kind of energy system that could actually put energy on the grid as opposed to take it off, which is what we do now.
Let's thank our speakers.